There are some points on a function of two variables. They're called local max and min. And finding where they are has been the ruin of many a poor boy. How God I know I'm one. There are some points on a function of two variables. They're called local max and min. And finding where they are has been the ruin of many poor boy. Oh God, I know I'm one. Alright, so in this video we will study local maxima and minima for functions of two variables. One of the main use of derivatives for functions of one variable was to find maxima and minima of functions and use this to solve optimization problems. So now we can ask whether we can do the same thing for functions of two variables. So here I have the graph of a function of two variables. So the first question is to find the maxima and the minima of the function. So for this I'd have to define what it means to be a maximum and a minimum of a function of two variables. So just looking at the graph here, it seems like this point and this point should probably be local minima for this function. And the second question is whether we can use partial derivatives to identify maximum, maxima, and minima for functions of two variables. So this is what we're going to address in this video. Let me start by defining the concept of maxima and minima for functions of two variables. So let f be a function of two variables x and y. We say that f has a local maximum at a point ab if f of xy is less or equal than f of ab for all xy near the point ab. And by near, what we mean here is for all xy in some disk centered at ab. And the number f of ab is called the local maximum value. Now we can define local minima in the same way. So we say that it has a local minimum at a point ab if f of xy is greater or equal than f of ab for all xy in some disk centered at ab, and we call f of ab the local minimum value. We can also talk about absolute maxima and minima. So if the inequalities hold for all xy not just near the point, but for all xy in the domain of the function, then we say that f has an absolute maximum or minimum at this point. Now if we go back to the function, the graph of the function that I had in the previous slide, so here I've zoomed near the 2 points where I said I expected them to be minima. So if we look at one of them here, then indeed I can find a disk here such that for all xy in this disk, the value of the function f of xy is greater or equal than the value of the function at the point ab. So we fall in the second case here. This is a local minimum for the function. And the same is true for the other point here. So I found two local minima for the functions. The value of the function at these 2 points is actually the same. So then we could ask whether these are absolute minima for the function, but for this I would have to tell you what the function actually is, because you need to check that the inequality is satisfied for all xy in the domain of the function. It turns out that for the function that I actually graphed here, it is true. These 2 points are absolute minima for the function. Alright, that's all cool, but how do we find the local maxima and minima of a function? Recall that in the case of one variables, we had a result that said that if a point is a local maximum or minimum for the function, then it must also be a critical point for that function, meaning that the first derivative of the function either vanishes or does not exist at this point. We have a similar statement for functions of two variables, so we first need to define the concept of critical points. So the critical points of a function are the points where either the first order partial derivatives both vanish, or at least one of them does not exist. And in this class we're going to focus mostly on the case where they exist and actually vanish. So now the statement is, if f has a local maximum or minimum at a point, and its first order partial derivatives exist at this point, then they must both vanish That is, it must be a critical point for the function. So why is this true? Well, it basically follows from the analogous statement in one variable. So let's see how that goes. So if we look at the partial derivative with respect to x, for example, the key is to define a new function of one variable g of x, which is obtained from f by keeping y equals to b fixed. And then by definition of partial derivatives, we know that the partial derivative of f with respect to x evaluated at ab is equal to the ordinary derivative g prime of the function g of x at x equals to a. And we also know that g prime of a calculates the slope of the tangent line for the graph of the function g of x at the point x equals to a. But this curve is nothing else than the curve on the surface here, which corresponds to keeping y equals b fixed. And in particular, if the point here is a local minimum for the surface, it is also a local minimum for the curve. And then by the statement in one variable, we know that if it is a local minimum, it must be a critical point for the function g of x. And because here we're assuming that derivatives exist, it follows that g prime of a must vanish. So in other words, the partial derivative with respect to x evaluated at ab must vanish. And of course, the same is true for the partial derivative with respect to y, but here we're talking about a different curve which corresponds to keeping x equals to a fixed on the surface. But again, the point must be a local minimum for that curve as well. So the partial derivative of the function with respect to y evaluated at ab must also vanish. There is also a nice geometric interpretation of this condition in terms of tangent planes. So recall that we can calculate the equation of the tangent plane to the graph of f at this point as follows. So we get z minus z naught, which is where z naught is equal to the value of the function at this point. And this is equal to the partial derivative with respect to x evaluated at this point, which is just 0 times x minus a, plus the same thing in y. And of course, the right-hand side here is simply 0. So we conclude that the tangent plane here is given by the equation z equals to a constant z naught. So in other words, the tangent plane at this point is horizontal. And that's a general statement. So for any local maximum or local minimum, if the partial derivatives exist, then the tangent plane, so if the tangent plane makes sense at this point, then it would always be horizontal. And you can see that it is true just by looking at the graph. So if you look at the local minimum here, indeed, the tangent plane will be given by a horizontal plane, z equals z naught, where z naught is the value of the function at this point. And you can convince yourself easily that this will always be true for any local maximum or minimum as long as the tangent plane makes sense at that point. However, as was the case for functions of one variables, while all local maxima and minima of functions are critical points for that function, the converse statement is not true. Not all critical points are local maxima or minima. So if you look back at the graph of the function that I've used in the previous slides, so here I've simply rotated the graph a little bit, you see that there is a special point here at which the tangent plane is horizontal. So saying that the tangent plane is horizontal is the same as saying that the partial derivatives of the function with respect to x and y vanish at this point. So in other words, it is a critical point for the function, but you see here that it is neither a local maximum nor a local minimum, because in one direction the value of the function goes up, while in the other direction it goes down. So it is not true that f of xy is greater or equal than or less or equal than f of ab for all xy in a disk center at this point, because in one direction it goes up, the other direction it goes down. So another example of such a point is if you look at two mountains and you look at a mountain pass between them. So beautiful picture here. I have two mountains and I have a hiker here which is going to the pass. So along the curve that the hiker is following, the pass looks like a local maximum because he's going up and then going down the other side. But along the curve in the direction of the mountains, this would look like a local minimum. So for the surface here, it is neither a local maximum nor a local minimum because it does not satisfy the condition. Okay, so we call such points in general saddle points for the obvious reason that the surface around such a point looks like a saddle. Now, since it is not true that all critical points are local maxima or minima, how do we determine whether a critical point is a local maximum or a local minimum? Fortunately, there is a test for that called the second derivative test, which is analogous to the second derivative test for functions of one variable, but it is slightly more complicated. So let f be a function of two variables and suppose that its second order partial derivatives are continuous on a disk centered at a point AB, and suppose as well that AB is a critical point. In other words, the first order partial derivatives both vanish at this point. Now define a function d of AB as being given by the second order partial derivative with respect to x times the second order partial derivative with respect to y minus the mixed partial derivative square. Then there are four cases to consider. If d is greater than 0 and the second order partial derivative with respect to x is greater than 0, then AB is a local minimum. If d is greater than 0 but the second order partial derivative with respect to x is less than 0, then AB is a local maximum. If d is less than 0, then AB is a saddle point, so it is neither a local maximum nor a local minimum. And if d is equal to 0, then the test fails and we cannot conclude anything. Now, I'm not going to prove the second derivative test in this video, but what I'll do is give you two examples where we use the second derivative test to analyze the critical function, the critical points of a function, and determine whether they are local minima, maxima, or saddle points. For my first example, let me consider the function f of xy equal to x squared plus y squared. So the first step is to determine the critical points of the function. So those are the points where both first order partial derivatives vanish. So for this function, the first order partial derivative with respect to x is equal to 2x, and the partial derivative with respect to y is equal to 2y. So the only point where they both vanish is the origin, the point 0, 0. Next, I need to determine whether this is a local maximum or a local minimum or a saddle point. So I use the second derivative test. So I need to calculate the second order partial derivatives. fxx is equal to 2. fyy is equal to 2. And the mixed partial derivative here is equal to 0. So I can calculate the function d that I introduced in the previous slide at the origin. So here, well, recall that this is given by fxx times fyy minus fxy squared. So at the origin here, I'll get 2 times 2 minus 0, which is equal to 4. So I am in the case where d is greater than 0 and fxx is also greater than 0. So if I look back at the statement of the second derivative test, I am in case A. So I can conclude that the origin here is a local minimum for the function. And indeed, we see that this is true because the function here is always positive. So if I look at any point near the origin, the value of the function will be greater or equal than the value function at the origin, which is 0. So indeed, the origin is a local minimum for the function. For my second example, let me consider the function f of xy equals to x squared minus y squared. So first I determine the critical points of the function. So I need to calculate the first order partial derivative. So fx is equal to 2x, fy is equal to minus 2y, from which I conclude that again there is a single critical point at the origin, and I want to determine whether it is a local maximum or a local minimum or a saddle point. So I use the second derivative test. So fxx is 2, fyy is minus 2, and the mixed partial derivative is again 0. So from this I conclude that d is equal to 2 times minus 2 minus 0, which is equal to minus 4. So I am in the case where d is less than 0, and if I look back at the second derivative test, I'm in case C, from which I conclude that the origin is a saddle point. So it is neither a local maximum nor a local minimum. And if you look at the function that you started with, it makes sense. Because if you approach the origin, say from the x-axis, so that means for y equals to 0, then you see that all the value of the function for any x near 0 will be in fact greater than the value at 0, which is 0. While if you approach from the y-axis, so it means you set x equals to 0, then the value of the function for any y close to 0 will be in fact less than the value of the function at the origin. So this is typical of a saddle point. So on one side it looks like a max, the other side it looks like a min. So it is neither a local max or min in general, it is a saddle point for the function of two variables.